Unsigned integers are kind of a weird topic when you first hear them. I'd imagine that most of you, like myself, when you first started to learn how to code, you were given a task to make a program to calculate some kind of monetary value, to see how much the store is making and to see how much the store owes their offshore loan sharks. But that's important to know. So why would we have a specific data type, I'm assuming using a strongly typed language, that removes the sign completely? Well, actually, unsigned integers came first, and even though we have our fancy signed integers, stick around to the end to find out why we'd want to go back to unsigned in the first place, especially in the realm of audio, and how a proper understanding of integers is needed to prevent an incident similar to the one on the 4th of June, 1996. To begin, we all know everything in a computer is binary. Same thing goes for integers, and the representation of integers usually lines up with what decimal value we get for our binary value. We all know ones place, tens place, hundreds place, with each place increasing by 10 to the power of the number of digits we already have. 10 to the power of 2 is 100. Binary is no different, but instead of 10, we have 2 as our base. Thereby, if we start with 2 to the power of 0 for our ones place, and if we had 2 to the power of 2, we'd go through a 2's place to a 4's place. And I'm actually going to add a 1 more bit or binary digit so we can get an actual data type called a nibble. That is actually its name. But to represent any set of bits as an integer, yeah, there are some conversion methods for binary to decimal, but really, intuitively, if we have a 1 in our 8's place, a 1 in our 4's place, and a 1 in our 1's place, 8 plus 4 plus 1 is 13, boom, there's our integer. And if we had a whole byte, thereby 8 bits, we'd have 256 possible integers we can represent using these amount of bits. Okay, so how do we go negative? Because if this is 13 in decimal, this can't also be negative 13. Those are complete opposites. And so engineers came up with a bunch of solutions, with 2 of the most famous ones being signed magnitude and 2's complement. And 2's complement reigns supreme on most hardware, but sign magnitude is still important. We'll start with sign magnitude because it's actually a lot easier to understand. It basically follows how we represent signs in decimal, with 1 bit being our sign bit, a positive sign being 0, and a negative sign being 1. The position of this bit is known as the most significant bit, since it's the highest bit position in our number. But in sign magnitude form, we're using that bit solely for our sign, with the other bits being whatever value we need. So if we wanted to represent negative 6, we can just make 6 using our first few bits and change the most significant bit, or MSB, to be 1. It's pretty simple. And to go back to how 8 bits gave us 256 values, we can actually figure out the range of values we are able to use. Unsigned values would give us a range between 0 to 2 to the power of n minus 1. And with our n being 8, we get the inclusive range of 0 to 255. But I thought you said 256 possible values. Yeah, I said 256 possible values, not up to 256, since 0 is our first value, not 1, thereby having 256 values. Sign magnitude gives us a range between negative 2 to the power of n minus 1 plus 1 to 2 to the power of n minus 1 minus 1. The minus 1 for our n being the bit we're sacrificing for the sign. If we had 8 bits, we'd have a range between negative 127 to positive 127, and still having 256 distinct values. But that's kind of a problem. Okay, let's say our magnitude is 0. So for our sign, we could put in sign magnitude, we end up having a negative value for 0 and a positive value for 0. That doesn't make sense since they're both 0, they're both the same value. Having these are redundant. And that's not all. Sign magnitude makes it pretty hard to add binary numbers. If we were to add negative 3 to 3, we'd get 0. If we were to add sign magnitude positive 3 and negative 3, and we do binary addition like we do normal addition, where if we get a number higher than 1, we carry the 1 over, we should get 0. But we don't though. Like, what is this, negative 6? So not only does sign magnitude give us redundant values, but addition don't even work. So hold on, now we've got 2's complement. 2's complement is a bit more complicated than sign magnitude. To represent negative 6, this is 6, this is the binary for 6. Okay, we could continue now, just clearing that up. Okay, we would have to flip all of the bits in our binary number, then add a 1 to get the 2's complement version of negative 6. This might seem random, but if we were to follow those 2 steps in every number, we get a binary number that when added to the original would result in 0. And like I said, that's kind of a prerequisite for how negative numbers work. Okay, again, just to be clear, this is -6 in the 2's complement system. This binary representation here is -6 and this is +6. Okay, just making sure you understand that. Okay, cool. If this feels like almost magic, think about what we're doing. Flipping every bit means that before we add 1, we'd get all 1s if we were to add them. And if we add 1 more bit, our answer overflows and the MSB gets discarded, leaving our answer to be all 0s, which is exactly what we want. However, now that we have this system, it becomes a bit obfuscated to say willy-nilly what would be our last or first number. Well, in the 2's complement system, the MSB for all positive numbers is 0 and the MSB for all negative numbers is 1. So it's still kind of like sign magnitude, with the magnitude part just being entirely different, so not like sign magnitude at all, really. The most negative number, depending on how many bits we have, would have 1 as its MSB with all 0s after it. And the most positive number would have 0 as its MSB with all 1s after it. Our range follows this rule, the lowest number being -2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. Now, as you could see, we are missing 1 positive number compared to our negative, and that's because in 2's complement, there's only 1 value for 0, which is aptly just all 0s. And since there's no more -0, our negative values get 1 more value all to itself. Thus, if we had 8 bits, we'd have the range -128 to 127, still giving us a total of 256 possible values. Whoa, okay, this is a bit weird. I mean, like, addition works, but that doesn't mean that subtraction does as well. Oh, look at that. But then multiplication still exists. Surely this can't work with multiplication as well. Oh, damn. And it's reasons like those why 2's complement is now the usual standard to represent signed integers. Unless stated otherwise, you're probably using 2's complement representation under the hood. Wait, so why do we still use unsigned integers? This 2's complement thing, while it is good, is a lot of work still. And computers these days have gotten pretty good at handling them, but why put your computer through more stress when you sometimes don't have to? Case 1.
I let a round wrap around every wrap around till it wrap around. This wrap around. I wrap around.
Unsigned numbers in a lot of implementations wrap around once they reach their limit as a result of overflow. Overflow meaning that if 1 was added to this number, the carryover bit would be too big for the design size of the data type or register size, meaning it'd be discarded. So the computer would just see it as 0. Overflow is pretty bad and was the cause of the Ariane Space Ariane 5 malfunction in 1996. The rocket costing $7 billion veered off course 40 seconds after launch, broke up, and eventually exploded, all because the computer behind the rocket overflowed its 16-bit range and caused a crash. Ironically, this was for 16-bit signed integers, and although the code was extensively tested for the Ariane 4 rocket, the Ariane 5's faster engines produced larger numbers that couldn't fit in the range of the computer, leading to one of the most expensive bugs in history. But if we know overflow is going to happen, then we can use it as an easy way to wrap around a certain range of numbers, and for it not to be undefined. This could be useful for something like a circular buffer used for a delay line and a reverb, or a certain audio driver. You can check out last links in the description. And adding numbers is a lot less expensive of a procedure than doing a whole modular to wrap around. Again, computers could handle a modular technically, even in pretty real-time systems like audio, like I've used it myself. But if you know you could just wrap around using your unsigned, well, you can just do that. Case 2, buffer sizes and indexes. Have you ever heard of a negative index? I rest my case. And a negative size of an audio buffer or any buffer really doesn't make sense. So we could just use an unsigned integer. Sure, we could just use a normal integer, but we also get way higher numbers we can reach with no trade-off in size of how many bits we're using. The normal int in C is 32 bits, which gives us an already impressive high number as our limit. But all we have to do is add an unsigned keyword and now our limit is... whoa! And yeah, we can't use signed numbers now, but if we're in a case when it just doesn't make sense for a number to be negative, we have a way higher set of numbers we can work with. Case 3, MIDI messages. MIDI messages are not negative, we don't need signed numbers, gives our computer less stress to work with, you get the idea. And in general cases where precise control over the bits itself is needed, unsigned integers can be pretty useful since we get more defined behavior than using signed. Like if I told you to do a bit shift using 2's complement, you can do it, but it definitely requires more thinking. So do yourself a favor and just use some unsigned integers. Wait, but what on earth is uint 8_t? In C and C++, just using int is implementation based, and the size of the int we get on different systems could be different. By saying unsigned integer 8_t, we're saying that everywhere this value will be 8 bits, and it should be treated as an unsigned number. There's also signed variations of this fixed variable type as well. You just normally see the unsigned version, well, at least I have. And there's also unsigned characters and signed characters as well. But listen, I know what you are. You're a CS student who's really just a kid that grew up on computers and was relatively good at math. And likes money. So you thought CS would work out for you, but no projects or direction paths feel particularly interesting to you. Especially since going down this path destroyed your creative side that sometimes you feel ashamed for admitting you have. So why not join us in this venture as an audio programmer, where you can be technically inclined to create wonderful audio creations and experiments. Something, you like money, this guy is one, he works at Apple now. If you'd also like to check out the building process of one of these audio applications, or to gain more information I couldn't fit here on unsigned characters and bit shifts and all that, then you can check out my Patreon, where we also got our first Patreon member. Woo! Shout out to Jackie Daralo, I hope I'm pronouncing that right. Thank you so much, it means a lot to me. You are very much appreciated. Instead, you don't want to spend any money, I get that. If you want to see an application of a wraparound cyclic buffer in action, then why not check out this video here.